Hello, and welcome. It's good to have you here in this quiet moment, wherever you are finding rest tonight. There is something almost magical about the way light bends through water, the way a simple rainstorm can suddenly paint the sky with color, and how the very same principles that create a rainbow above a field are woven into the fabric of everything we see. These aren't mysteries reserved for distant laboratories or complex equations. They're happening all around you, in every droplet, every glass of water, every moment light decides to slow down and reveal its hidden nature. You can let your shoulders settle, if you'd like. There's no urgency here. I know you might be tired, perhaps winding down from a long day, or simply looking for a gentle place to let your thoughts drift. That's perfectly fine. You're welcome to close your eyes whenever you wish, or simply let your gaze soften as we move through these ideas together. If these journeys bring you comfort, you're welcome to return anytime. There will always be more quiet explorations waiting. So let's begin with something simple and beautiful. Let's begin with light itself, and what happens when it meets the world. Light, in its purest form, travels in straight lines. It moves through the emptiness of space at a speed so immense, it's almost beyond imagining. Nearly 300 million meters every second. But light, for all its speed, is also remarkably gentle in how it interacts with matter. When it encounters something new, something denser than the vacuum it's been racing through, it doesn't simply crash or stop. Instead, it bends. This bending has a name. We call it refraction, and it's one of the most fundamental behaviors of light, one that shapes nearly everything we perceive about color, depth, and beauty in the world around us. Refraction happens because light changes speed when it moves from one material to another. Imagine you're walking briskly across a smooth wooden floor, and suddenly you step on a thick carpet. Your pace slows, doesn't it? Your stride adjusts. Light does something similar. When it moves from air into water, or from air into glass, it slows down. And when light slows down at an angle, it bends. The amount of bending depends on how much the light slows. Every transparent material has what scientists call a refractive index, a number that tells us how much slower light moves through it compared to empty space. Air has a refractive index very close to 1, meaning light barely slows at all. Water's refractive index is about 1.33. Glass can be 1.5 or higher, depending on its composition. The higher the number, the more the light bends. This bending is predictable, mathematically precise, and it follows a principle discovered centuries ago by a Dutch mathematician named Willebroord Snellius. His law, now called Snell's law, describes exactly how much light will bend based on the materials it's moving between and the angle at which it arrives. It's a quiet, elegant equation that governs the behavior of every rainbow, every lens, every glint of light through a window. But let's stay with something you can picture easily. Imagine a beam of sunlight, pure and white, entering a triangular piece of glass, a prism. The light hits the surface at an angle, and as it crosses from air into glass, it slows and bends inward toward what we call the normal, an imaginary line perpendicular to the surface. Now here's where something wonderful happens. White light, the kind that pours from the sun or a light bulb, isn't actually a single thing. It's a mixture, a blend of many colors, each with its own wavelength. Red light has a longer wavelength, around 700 nanometers. Violet light has a shorter wavelength, around 400 nanometers. And between them lie all the colors you know: orange, yellow, green, blue, indigo. When white light enters the prism, each of these colors slows down by a slightly different amount. Violet light, with its shorter wavelength, slows more than red light. Because it slows more, it bends more. Red light, slowing less, bends less. And so the single beam of white light spreads out into a spectrum, a fan of colors, each taking its own path through the glass. This spreading is called dispersion. It's the reason prisms create rainbows. It's the reason a glass of water on a sunny windowsill can throw colored patches onto the wall. It's the reason rainbows exist at all. Let's move now to the sky, to the moment after a rainstorm when the air is still full of moisture and the sun breaks through the clouds. Each tiny droplet of water hanging in the atmosphere acts like a miniature prism, but with a shape that's far more interesting: a sphere. When sunlight enters a raindrop, it refracts, bending as it crosses from air into water. The light spreads into its spectrum of colors. Then, instead of passing straight through, much of that light hits the back inner surface of the droplet and reflects, bouncing forward again. As it exits the front of the droplet, it refracts once more, bending again as it moves from water back into air. This double refraction and single reflection send the light back toward the direction it came from, but at a specific angle. For red light, that angle is about 42 degrees from the line between the sun and the shadow of your head. For violet light, it's about 40 degrees. The other colors fall between. So when you see a rainbow, you're seeing millions of droplets, each one sending a specific color to your eye based on its position in the sky. The droplets that appear red are higher up at that 42-degree angle. The droplets that appear violet are lower at 40 degrees. Every droplet is refracting sunlight, but you only see the color that happens to bend toward your eye at just the right angle. This is why rainbows are always curved. The set of all droplets at a given angle from the antisolar point, the spot directly opposite the sun from your perspective, forms a circle. You see an arc because the ground blocks the lower half. But if you were in an airplane or standing on a mountain with mist below you, you might see a full circular rainbow, a complete ring of color hanging in the air. And here's something even more calming to consider. Every person sees their own rainbow. The rainbow you see is made of light from droplets in a specific position relative to you and the sun. Someone standing beside you sees light from different droplets at slightly different angles. Your rainbow, and there's overlap, but they are not identical. Each rainbow is personal, a private conversation between you, the sun, and the rain. Rainbows are also always opposite the sun. If the sun is behind you and to your left, the rainbow will be in front of you and to your right. The center of the rainbow's arc always lies on the line extending from the sun through your head to the antisolar point. This is why you rarely see rainbows at midday when the sun is high. The antisolar point would be below the horizon, and there would be no sky for the rainbow to appear in. The best rainbows come in early morning or late afternoon, when the sun is low and the arc can rise high into the sky. Sometimes, if the conditions are just right, you can see a second rainbow outside the first. This secondary rainbow is fainter, and its colors are reversed, with red on the inside and violet on the outside. It forms when light reflects twice inside the raindrops instead of once. That extra reflection flips the order of the colors and sends the light out at a wider angle, around 50 to 53 degrees. The sky between the primary and secondary rainbows often appears darker than the sky outside them. This region is called Alexander's Band, named after Alexander of Aphrodisias, a Greek philosopher who described it nearly 2,000 years ago. The darkness occurs because the angles between the two rainbows correspond to directions where very little light is refracted back toward your eyes. It's a shadow cast by geometry itself. There are even rarer rainbows, ones that require very specific conditions. Supernumerary rainbows are faint, pastel-colored bands that sometimes appear just inside the primary rainbow. They form because light behaves not only as rays, but also as waves. When waves of light overlap and interfere with each other, they can strengthen or cancel out, creating those delicate extra arcs of pink and green. Reflected rainbows can appear when sunlight reflects off a body of water before reaching the raindrops. This creates a second light source, and thus a second rainbow that seems to rise from the water's surface. Reflection rainbows are rare and require a large, calm body of water and just the right observer position. Moonbows, or lunar rainbows, form at night when the moon is bright enough to create the same refractive effects in water droplets. They are much dimmer than solar rainbows and often appear almost white to our eyes because our color vision doesn't work well in low light. But long exposure photographs reveal their full spectrum, just as vivid as any daytime rainbow. Fogbows appear in fog rather than rain. Because fog droplets are much smaller than raindrops, they diffract light in addition to refracting it. This diffraction smears out the colors, and fogbows often appear as broad, ghostly white arcs with just a hint of red on the outer edge and blue on the inner edge. They're sometimes called white rainbows. All of these phenomena, from the brightest primary rainbow to the faintest fogbow, arise from the same basic principles. Light slows, bends, reflects, and spreads into colors. The specifics change with droplet size, light source, and observer position, but the underlying physics remains constant and calm. Let's think smaller now, closer to home. You don't need a rainstorm to see refraction. You see it every time you look at a straw in a glass of water. The straw appears bent or broken at the surface. This happens because light traveling from the submerged part of the straw to your eye bends as it exits the water. Your brain assumes light travels in straight lines, so it traces the bent rays backward and perceives the straw as being in a different position than it truly is. This same effect makes pools look shallower than they are. Light reflecting off the bottom of the pool bends upward as it exits the water, reaching your eyes at a steeper angle. Your brain interprets this as the bottom being closer than it is. It's a gentle illusion, one that's caused countless misjudgments of depth, but also countless moments of wonder. Refraction also explains why the sun appears slightly flattened when it's near the horizon. The atmosphere is denser near the ground, and light from the lower part of the sun refracts more than light from the upper part. This compresses the sun's image vertically, turning a perfect circle into an oval. The effect is subtle, but once you know to look for it, you'll see it every sunset. Even more remarkable, refraction allows you to see the sun before it actually rises and after it actually sets. When the sun is just below the horizon, its light still reaches you because the atmosphere bends it over the curve of the Earth. This atmospheric refraction extends daylight by several minutes at each end of the day, a small gift from the physics of light. Mirages are another beautiful consequence of refraction. On a hot day, the air just above a paved road heats up and becomes less dense than the cooler air above it. Light from a sky traveling downward toward the road bends gradually as it passes through these layers of different density, curving upward before it reaches the ground. Your brain, tracing the light backward in straight lines, perceives a shimmering reflection of the sky on the road. It looks like water, but it's just light taking a curved path through the air. Superior mirages occur when the air near the ground is colder than the air above, often over icy surfaces or cold oceans. In these conditions, light bends downward, and distant objects can appear elevated, stretched, or even inverted. Ships can seem to float above the horizon. Entire coastlines can appear in the sky. These mirages have inspired legends of ghost ships and floating cities, but they're simply light moving through layers of air with different temperatures. The twinkling of stars is also a form of refraction. Starlight travels through space in a straight, steady beam, but when it enters Earth's atmosphere, it passes through pockets of air with slightly different densities, temperatures, and motions. Each pocket bends the light a tiny bit, and because the air is constantly moving, the direction of bending changes moment by moment. The star's light shifts position and brightness rapidly, and we see it as a twinkle. Planets, being closer and appearing as small disks rather than points, twinkle much less because their light comes from many points averaged together. Refraction is even essential to how your eyes work. The front surface of your eye, the cornea, is curved and denser than air. When light enters your eye, it refracts, bending inward. The lens inside your eye refracts the light further, fine-tuning the focus. Together, the cornea and lens bend light so that it converges on your retina, forming a clear image. Without refraction, you couldn't see it all. Every moment of vision is a moment of light bending. Eyeglasses and contact lenses work by adding extra refraction to correct for imperfections in your eye shape. If your eye focuses light in front of the retina, you're nearsighted, and a diverging lens spreads the light slightly before it enters your eye. If your eye focuses light behind the retina, you're farsighted, and a converging lens brings the light together sooner. It's all about adjusting the path light takes, bending it just a little more or a little less. Cameras use the same principles. A camera lens is a carefully shaped piece of glass or plastic designed to refract light from the scene in front of it and focus that light onto a sensor or piece of film. The curvature of the lens, the type of glass, and the arrangement of multiple lens elements all control how the light bends and how the image forms. Every photograph you've ever seen exists because of refraction. Microscopes and telescopes extend human vision by using multiple lenses to refract light in precise ways. A microscope takes light from a tiny object and bends it so that it appears larger when it reaches your eye. A telescope takes light from a distant object, which arrives in nearly parallel rays, and bends it to form a magnified image. Both instruments are, at their core, tools for controlling refraction. Fiber optic cables, the technology that carries much of the world's internet traffic, rely on a special form of refraction called total internal reflection. When light inside a material hits the boundary with a less dense material at a steep enough angle, it doesn't refract out. Instead, it reflects entirely back inward. This allows light to travel through a thin glass fiber, bouncing off the walls again and again, over distances of many kilometers without escaping. Information encoded in pulses of light can travel around the world this way, guided by the principles of refraction. Diamonds sparkle because of refraction and total internal reflection. Diamond has a very high refractive index, around 2.4, meaning light slows dramatically and bends sharply when it enters. The angles of a well-cut diamond are designed so that light entering the top refracts inward, reflects off the internal facets multiple times, and then refracts back out through the top, dispersing into flashes of color. The fire of a diamond, those flashes of red and blue and green, comes from dispersion, the same effect that creates rainbows. Water droplets on a spider's web can act like tiny lenses, each one refracting light and focusing it. On a dewy morning, a web can seem to glow, each droplet catching sunlight and bending it toward your eye. The web itself might be nearly invisible, but the refracted light makes it shimmer. The green flash is a rare optical phenomenon that can occur just as the sun sets or rises. Because the atmosphere refracts different colors by different amounts, the top edge of the sun can briefly appear green for a second or two. It requires a clear horizon and stable atmospheric conditions. But when it happens, it's a vivid reminder that the sun's white light is always a mixture, always ready to split into colors. Rainbows on soap bubbles and oil slicks are not caused by refraction in the same way as sky rainbows. Instead, they come from thin film interference, where light waves reflecting off the top and bottom surfaces of a thin layer combine and amplify certain colors while canceling others. But refraction still plays a role, as the light must enter and exit the film, bending slightly each time. Prisms have been used for centuries to study light. Isaac Newton famously used a prism in a darkened room to split sunlight into a spectrum, proving that white light is composite. He then used a second prism to recombine the colors back into white light, demonstrating that the prism wasn't adding color, but revealing what was already there. This experiment, simple and elegant, changed our understanding of light forever. Rainbows have inspired countless myths and stories. In many cultures, they're seen as bridges between worlds, symbols of hope, or promises from the divine. The Norse believed the rainbow was Bifrost, a bridge connecting Earth to Asgard. In Irish folklore, leprechauns hide pots of gold at the rainbow's end. These stories reflect our deep human response to beauty and mystery, even as science offers its own kind of wonder. The colors of the rainbow are often remembered with mnemonics like Roy G. Biv, standing for red, orange, yellow, green, blue, indigo, and violet. But in truth, the spectrum is continuous. There are no hard boundaries between colors, just a smooth gradation of wavelengths. Indigo is sometimes considered a separate color and sometimes not, depending on cultural and historical context. What matters is the flow, the seamless transition from one hue to the next. Human eyes have 3 types of color receptors, called cones, each sensitive to different ranges of wavelengths. One type responds most to long wavelengths, which we perceive as red. Another responds to medium wavelengths, which we perceive as green. The third responds to short wavelengths, which we perceive as blue. Every color you see is a combination of signals from these 3 receptors. A rainbow stimulates them in shifting proportions, creating the sensation of a full spectrum. Some animals see refraction and color differently than we do. Birds often have 4 types of cones and can see into the ultraviolet range. Flowers that look plain to us may have vivid ultraviolet patterns visible to bees and birds. Mantis shrimp have 16 types of color receptors and perceive a range of wavelengths and polarizations far beyond human experience. Refraction affects their vision too, but in ways we can barely imagine. Rainbows can appear in unexpected places. The spray from a waterfall can create rainbows on sunny days. A garden hose with a fine mist can summon a small rainbow in your backyard. Even the spray from a whale's blowhole, catching the light just right, can shimmer with color. Wherever there are droplets in sunlight, refraction is ready to paint the air. Circular rainbows, as seen from airplanes, are sometimes called glories when they appear around the shadow of the plane on clouds below. Glories are related to rainbows, but involve more complex scattering and interference effects. Still, refraction is part of the process, bending light within the tiny cloud droplets. The color red always appears on the outer edge of a primary rainbow because red light refracts the least and exits the droplet at the widest angle. Violet appears on the inner edge because it refracts the most. This order is reversed in secondary rainbows because of the extra internal reflection. Refraction also affects how we perceive the size of objects underwater. A fish in an aquarium looks slightly larger and closer than it actually is because light from the fish bends as it exits the water and enters the air, then the glass, then the air again. Your brain compensates, but not perfectly. Photographers sometimes use polarizing filters to reduce glare from water or glass. Glare is caused by light reflecting off surfaces, and some of that light becomes polarized, meaning its waves oscillate in a single plane. A polarizing filter blocks light oscillating in certain directions, reducing reflections and allowing more of the refracted light from beneath the surface to reach the camera. Rainbows never actually exist in a fixed location. They're not objects you can walk to or touch. They're patterns of light, angles, and perception. As you move, the rainbow moves with you, always maintaining that precise angular relationship with the sun in your eyes. Chasing a rainbow is chasing geometry itself. The speed of light in a vacuum is constant, but in materials, it slows. In water, light travels at about 75% of its vacuum speed. In diamond, it slows to less than half. This slowing is what causes refraction. And it's also why materials with higher refractive indices create more dramatic optical effects. Refraction can create caustics, those bright, shifting patterns of light you see on the bottom of a swimming pool or on a table beneath a glass of water. Caustics form when refracted or reflected light rays converge and concentrate in certain areas, creating bright curves and loops. They're a side effect of the way curved or wavy surfaces bend light unevenly. The way light moves through a prism reveals something profoundly gentle about the universe. When a beam of white light enters the triangular glass, it doesn't simply pass through unchanged. Instead, it spreads into a spectrum, a fan of colors that stretches from deep red to violet, each wavelength taking its own path according to how much it bends. The red light, with its longer wavelengths, bends the least. The violet light, with wavelengths nearly half as short, bends the most. Between them lie orange, yellow, green, blue, and indigo, each occupying its precise position in this quiet parade of color. The prism doesn't add these colors. It merely separates what was always there, hidden in the white light, waiting to be revealed. Isaac Newton performed this experiment in a darkened room in 1666, allowing a single shaft of sunlight to pass through a small hole in his window shutter. He placed a glass prism in the beam's path and watched as the white light transformed into a spectrum on the opposite wall. He called this spread of colors the spectrum, from the Latin word for appearance or apparition. What captivated Newton wasn't just the beauty of the colors, but the fact that when he used a second prism to recombine them, they merged back into white light. This told him something essential. White light is not pure or simple, but a mixture of all visible colors traveling together. The reason different colors bend by different amounts has to do with the speed of light in glass. Light travels at about 299,792 kilometers per second in a vacuum, but when it enters glass, it slows down. The amount of slowing depends on the wavelength. Violet light slows more than red light when entering glass, and this difference in speed causes the difference in bending. The refractive index of glass for violet light is higher than for red light, typically around 1.53 compared to 1.51. These small differences accumulate as the light travels through the prism, spreading the colors apart in a process called dispersion. Dispersion is the reason we see rainbows, and it's also the reason diamonds sparkle with such varied colors. A diamond's high refractive index, around 2.42, means light slows dramatically when entering the stone. Combined with the diamond's carefully cut angles, this creates strong dispersion, splitting white light into flashes of spectral color. Gemologists call this property fire, and it's one of the qualities that makes diamonds so prized. Different gemstones have different amounts of fire depending on their refractive indices and dispersion characteristics. Cubic zirconia, for instance, has even more fire than diamond, which is one reason it can be distinguished by experts. It sparkles almost too much. Water droplets in the atmosphere act as countless tiny prisms, each one refracting and reflecting sunlight. When light enters a raindrop, it slows and bends. Some of this light reflects off the back interior surface of the drop, then refracts again as it exits. The two refractions, combined with the internal reflection, spread the light into colors and direct them back toward the observer at specific angles. Red light exits the drop at an angle of about 42 degrees from the antisolar point, the point directly opposite the sun from the observer's perspective. Violet light exits at about 40 degrees. This 2-degree difference creates the arc of the rainbow. The rainbow you see is unique to your position. Someone standing beside you sees a different rainbow, formed by different droplets. The rainbow is not an object in a fixed location. It's a pattern of light that depends entirely on the geometry between the sun, the water droplets, and your eyes. If you move, the rainbow moves with you. If you try to approach it, it recedes. This is why the end of a rainbow can never be reached. It's not a place, but a relationship between light, water, and perspective. Every rainbow is actually a full circle, though we usually see only an arc. The ground blocks the lower half from view when we stand on the Earth's surface. But from an airplane, or from a mountaintop with mist in the valley below, you can sometimes see a complete circular rainbow. The center of this circle is always at the anti-solar point, the shadow of your head. Some pilots and mountain climbers have witnessed these full circle rainbows and described them as among the most serene sights in nature, a perfect ring of color floating in the air. The colors of a rainbow always appear in the same order: red on the outside of the arc, violet on the inside. This order is determined by the physics of refraction and cannot be reversed. Sometimes you might see a second, fainter rainbow outside the first. This is a double rainbow, formed by light that reflects twice inside the raindrops before exiting. Because of the extra reflection, the colors in the secondary rainbow are reversed: violet on the outside, red on the inside. The secondary rainbow is always fainter because some light is lost with each reflection inside the droplet. Between the primary and secondary rainbows, there's often a darker band of sky. This region is called Alexander's Band, named after Alexander of Aphrodisias, who described it in the 2nd century. The darkness occurs because raindrops don't send light toward this region. The angles don't work out geometrically. Light is concentrated in the rainbow arcs and relatively absent in the space between them. On a bright rainbow day, if you look carefully, you can see this band of darker sky, a gentle reminder of the precise geometry governing where light does and doesn't travel. Supernumerary rainbows are faint, pastel-colored bands that sometimes appear just inside the primary rainbow. These delicate arcs of pink, green, and purple are caused by interference, a wave phenomenon where light waves overlap and either strengthen or cancel each other. When raindrops are very uniform in size, typically less than a millimeter across, the light waves exiting them can interfere constructively and destructively, creating these extra bands. Supernumerary arcs are more common than many people realize, but they require careful observation and the right conditions: small, uniform droplets, and a keen eye. Fog bows are the pale cousins of rainbows, appearing as broad, white or faintly colored arcs in fog. Fog consists of much smaller water droplets than rain, typically between 10 and 100 micrometers in diameter. These tiny droplets still refract and reflect light, but because they're so small, diffraction becomes significant. Diffraction blurs the colors together, creating a bow that's mostly white with perhaps faint hints of color at the edges. Fog bows are sometimes called white rainbows or cloud bows, and they appear most often in mountain fog or sea spray, glowing softly against the gray mist. Moon bows, or lunar rainbows, formed by the same principles as solar rainbows, but with moonlight instead of sunlight. Because moonlight is much dimmer than sunlight, about 400,000 times dimmer, moonbows are faint and rare. They appear most often near waterfalls, where mist is abundant and persistent, or during particularly bright, full moons and rainy conditions. To the human eye, moonbows often appear nearly colorless, glowing white or pale gray, because our eyes' color-sensing cone cells don't work well in low light. But long-exposure photographs reveal that moonbows contain the same spectrum of colors as daytime rainbows, just too dim for us to perceive directly. The brightness of a rainbow depends on the size of the water droplets. Larger drops, around 1 to 2 millimeters in diameter, produce the brightest, most vivid rainbows with well-defined colors. Smaller drops create fainter bows with more washed-out colors. Very small drops, as in fog, create fog bows with little color at all. This is because larger drops reflect more light and produce less diffraction, allowing the colors to remain distinct. The ideal conditions for a vivid rainbow are large, uniform raindrops, bright sunlight, and a dark background sky, often found when the sun breaks through just after a heavy rain shower. Rainbows can appear in sea spray, fountain mist, garden sprinklers, and even in the spray from a whale's blowhole. Anywhere water droplets are suspended in the air with sunlight shining through them, a rainbow can form. Some of the most reliable places to see rainbows are near large waterfalls, where mist is constantly present. Niagara Falls, Victoria Falls, and Yosemite Falls are famous for their frequent rainbows, visible almost any sunny day. Indigenous peoples living near these waterfalls have incorporated rainbows into their stories and spiritual traditions for thousands of years, seeing them as bridges, pathways, or messages. The width of a rainbow's arc depends on the size of the sun's disk in the sky. Because the sun isn't a point source, but a disk about half a degree wide, the light comes from slightly different angles. This causes each color band in the rainbow to be about half a degree thick, giving the rainbow its characteristic width. If the sun were smaller in the sky, rainbows would be thinner. If it were larger, they'd be broader and perhaps less distinct. The sun's size, as seen from Earth, is one of those cosmic coincidences that makes our rainbows appear just as they do. Refraction doesn't only create beauty, it also serves essential functions in nature and technology. The lenses in our eyes use refraction to focus light onto the retina, allowing us to see clearly. The cornea, the clear front surface of the eye, does most of this refracting, bending light as it enters. The lens behind the cornea fine-tunes the focus, changing shape to adjust for near or distant objects. This process, called accommodation, relies entirely on the principle of refraction, changing the curvature of a surface to change how much light bends. When light passes from air into water, it bends toward the normal, the imaginary line perpendicular to the surface. This is why a straight stick appears bent when you place it partially in water. The part of the stick underwater appears shifted from where it would be if the stick were straight. Your brain interprets the light rays as traveling in straight lines, so it perceives the stick as bent at the water's surface. This same effect makes swimming pools look shallower than they really are. The bottom of the pool appears closer because the light rays from it bend away from the normal as they exit the water, reaching your eyes at a steeper angle than they would in air. Fishermen and spearfishers learn to account for refraction when aiming at fish underwater. A fish isn't where it appears to be. It's deeper and farther away than it looks. The amount of displacement depends on the viewing angle. Looking straight down, there's little distortion, but at shallow angles, the displacement becomes significant. Experienced spearfishers learn to aim below and beyond the apparent position of the fish, compensating instinctively for the bending of light at the water surface. Mirages are another beautiful consequence of refraction, occurring when light bends as it passes through air layers of different temperatures. On a hot day, the air just above a paved road becomes much hotter than the air higher up. Light from the sky travels downward through these layers, speeding up as it enters the hotter, less dense air near the ground. This causes the light to curve upward, bending away from the normal. To an observer, it appears as if there's a pool of water on the road ahead, reflecting the sky. What you're actually seeing is refracted skylight that has curved upward before reaching your eyes. As you approach, the mirage recedes, always staying ahead of you. Superior mirages occur when the air near the ground is colder than the air above, the opposite of the usual situation. This happens often over cold water or ice. Light curves downward in these conditions, causing distant objects to appear elevated, stretched, or distorted. Ships can seem to float above the horizon, or distant coastlines can appear closer and higher than they really are. In extreme cases, superior mirages can create complex, layered images, with multiple distorted versions of the same object stacked vertically. These are sometimes called Fata Morgana mirages. named after the sorceress Morgan Le Fay from Arthurian legend, who was said to create castles in the air. The green flash is a rare optical phenomenon visible just as the sun sets or rises over a clear, distant horizon. For a second or two, the very top of the sun's disk appears to flash bright green. This happens because the atmosphere acts like a weak prism, refracting sunlight and spreading it slightly into colors. Red light, which bends least, disappears below the horizon first. Green and blue light, which bend more, lingers slightly longer. Blue light is usually scattered away by the atmosphere, leaving green as the last visible color. The green flash requires a very clear atmosphere and an unobstructed horizon, making it most common over the ocean. Seeing one is considered good luck by sailors, a small gift from the physics of light. Atmospheric refraction also affects the apparent positions of stars and planets. When you look at a star near the horizon, you're not seeing it where it actually is. The Earth's atmosphere bends the starlight, making the star appear higher in the sky than it would be without an atmosphere. At the horizon, this displacement is about half a degree, roughly the width of the sun or moon. As you look higher in the sky, the effect diminishes, becoming negligible at the zenith, the point directly overhead. Astronomers must account for atmospheric refraction when making precise measurements of celestial positions. This refraction also extends the length of the day slightly. When the sun appears to be just touching the horizon at sunset, it has actually already dipped below it. The atmosphere bends the sunlight, allowing you to see the sun for a few extra minutes. Similarly, at sunrise, you see the sun before it has actually risen above the geometric horizon. This effect adds about 6 minutes to the daylight each day, 3 minutes at sunrise and 3 at sunset. At higher latitudes, where the sun rises and sets at shallower angles, the effect is even more pronounced. The twinkling of stars, called scintillation, is caused by refraction in turbulent air. As starlight passes through the atmosphere, it encounters pockets of air with slightly different temperatures and densities. Each pocket bends the light a little differently, and because these pockets are constantly moving and changing, the light's path shifts rapidly. This makes the star appear to twinkle, changing slightly in brightness and position several times per second. Planets twinkle much less than stars because they're not point sources. They have a small but measurable disk. The light from different parts of the planet's disk averages out the twinkling, making planets appear to shine steadily. Astronomers build observatories on high mountains partly to get above as much of the atmosphere as possible, reducing the distorting effects of refraction and turbulence. Mauna Kea in Hawaii, at about 4,200 meters above sea level, is above 40% of the atmosphere and most of the water vapor. The air is thinner, drier, and more stable, allowing telescopes to capture sharper images. Even better is placing telescopes in space, entirely above the atmosphere. The Hubble Space Telescope, orbiting Earth, sees stars without any atmospheric interference. No twinkling, no refraction, just pure, steady light. Optical fibers use refraction to guide light over long distances. An optical fiber is a thin strand of glass or plastic, typically thinner than human hair. Light enters one end and travels through the fiber by repeatedly reflecting off the inner surface. This is possible because of total internal reflection, which occurs when light tries to exit a material at a shallow angle, and the refractive index difference is great enough. Instead of refracting out, the light reflects back in, staying trapped inside the fiber. This allows light to travel through the fiber even if it bends and curves, carrying information at nearly the speed of light. The internet, phone calls, and cable television all rely on optical fibers. Pulses of light represent digital data, flickering on and off millions or billions of times per second. These pulses travel through fiber optic cables spanning continents and crossing oceans, carrying vast amounts of information with minimal loss. The light used is usually infrared, with wavelengths around 1,550 nanometers, because glass is most transparent at this wavelength. A single fiber can carry multiple wavelengths simultaneously, each one a separate channel of data, multiplying the fiber's capacity. This technique, called wavelength division multiplexing, is possible because different wavelengths refract and behave slightly differently, allowing them to be separated and recombined. Lenses are perhaps the most familiar application of refraction. A converging lens, thicker in the middle than at the edges, bends parallel light rays inward, bringing them together at a focal point. This is the principle behind magnifying glasses, camera lenses, eyeglasses for farsightedness, and the objective lenses of telescopes. A diverging lens, thinner in the middle, bends parallel rays outward, making them spread apart as if they came from a focal point behind the lens. These are used in eyeglasses for nearsightedness and in certain optical instruments to correct aberrations. The focal length of a lens depends on its curvature and its refractive index. A lens made of glass with a higher refractive index bends light more sharply, creating a shorter focal length for the same curvature. This is why high-quality camera lenses often use special types of glass with carefully chosen refractive properties. By combining multiple lens elements made of different glasses, lens designers can correct for chromatic aberration, the tendency of different colors to focus at slightly different points. This creates sharper, clearer images with accurate colors. Eyeglasses correct vision by adding refraction to compensate for imperfections in the eye's own focusing system. If your eye focuses light in front of the retina, you're nearsighted, and you need a diverging lens to spread the light slightly before it enters your eye. If your eye focuses light behind the retina, you're farsighted, and you need a converging lens to bring the light together sooner. Astigmatism, caused by an irregularly shaped cornea, is corrected with cylindrical lenses that refract light more in one direction than another. The precise prescriptions for eyeglasses are determined by measuring how light refracts through your eye and calculating the additional refraction needed to focus it correctly on the retina. Contact lenses work on the same principle, but they sit directly on the eye's surface, floating on a thin layer of tears. Because they're closer to the eye's optical system, the prescriptions differ slightly from eyeglasses for the same person. The tear layer between the contact lens and the cornea also plays a role in the refraction, effectively becoming part of the lens system. Modern contact lenses are made from materials that allow oxygen to pass through to the cornea, keeping the eye healthy while still providing the necessary refractive correction. Microscopes use multiple lenses to magnify tiny objects. The objective lens, close to the specimen, creates a magnified real image. The eyepiece lens then magnifies this image further, allowing you to see details far smaller than the unaided eye could resolve. The total magnification is the product of the objective's magnification and the eyepiece's magnification. A microscope with a 40x objective and a 10x eyepiece provides 400x magnification. But magnification alone isn't enough. Resolution, the ability to distinguish fine details, depends on the wavelength of light and the quality of the lenses. Shorter wavelengths, like blue or ultraviolet light, provide better resolution than longer wavelengths like red. Telescopes also use refraction, at least in refracting telescopes, which employ large objective lenses to gather and focus light from distant objects. The larger the objective lens, the more light it collects, allowing fainter objects to be seen. The focal length of the objective determines the telescope's magnification when combined with an eyepiece. Refracting telescopes were the first type developed, with Galileo using one to observe the moons of Jupiter in 1610. However, very large refracting telescopes are difficult to build because large lenses are heavy and can sag under their own weight, distorting the image. The largest refracting telescope ever built, at Yerkes Observatory in Wisconsin, has an objective lens 1 meter in diameter. Most large modern telescopes use mirrors instead, but the principle of gathering and focusing light remains the same. Cameras use lenses to focus light onto a sensor or film, creating an image. The lens projects an inverted, real image onto the sensor, just as the lens in your eye projects an image onto your retina. The aperture, an adjustable opening in the lens, controls how much light enters. A wider aperture lets in more light, useful in dim conditions, but also creates a shallower depth of field, meaning only a narrow range of distances is in sharp focus. A smaller aperture increases depth of field, but requires more light or a longer exposure. Photographers balance these factors to achieve the desired effect, using refraction to shape light into art. Prisms are used in binoculars to fold the light path, making the device more compact. Light enters the objective lens, bounces off internal prisms, and exits through the eyepiece. The prisms also flip the image right side up, correcting the inversion caused by the lenses. There are different prism designs, poro prisms and roof prisms, each with advantages. Poro prisms create a wider, offset design that provides better depth perception. Roof prisms allow a more streamlined, straight barrel design. Both rely on total internal reflection within the prisms, a consequence of refraction at boundaries. Raindrops aren't the only natural source of rainbows. Ice crystals in the atmosphere create halos, arcs, and other optical phenomena through refraction. A 22-degree halo, a ring of light around the sun or moon, forms when light refracts through hexagonal ice crystals in high, thin cirrus clouds. The crystals act like tiny prisms, bending the light by about 22 degrees. The halo appears as a circle at this angular distance from the sun, often with a faint reddish inner edge and a bluish outer edge. These halos are fairly common, but many people don't notice them because looking near the sun is uncomfortable. Sundogs, also called parhelia, are bright spots that appear on either side of the sun at the same elevation, often at the same 22-degree distance as the halo. They form when hexagonal ice crystals are oriented horizontally, floating in the air like tiny plates. Sunlight enters through one vertical face of the crystal and exits through another, refracting and creating concentrated spots of light. Sundogs are often more colorful than halos, showing distinct reds, oranges, and yellows. They're most vivid when the sun is low on the horizon, and they can be bright enough to look like two additional suns flanking the real one. The circumzenithal arc is one of the most beautiful ice crystal phenomena, sometimes called the smile in the sky. It appears as a bright, colorful arc high above the sun, near the zenith, curving upward like an upside-down rainbow. It forms when sunlight enters the flat top face of horizontal plate-shaped ice crystals and exits through a vertical side face, refracting through 90 degrees. The colors are pure and vivid, often more saturated than a rainbow's, and the arc is usually short-lived, appearing only when the sun is at the right angle. Because it's high in the sky, many people never notice it, but once you know to look for it, you might see it several times a year. Light pillars are vertical shafts of light extending above or below the sun or moon, or even from artificial lights. They form when light reflects off the flat surfaces of ice crystals floating horizontally in the air. The crystals act like tiny mirrors, reflecting light toward the observer. Light pillars are most common in cold weather, when ice crystals form in the lower atmosphere. They can appear above streetlights, creating glowing columns reaching into the night sky, a quiet intersection of human light and atmospheric physics. Refraction affects how we perceive depth underwater. When you look into an aquarium, the glass and water both refract light, making fish and decorations appear closer and larger than they are. Diverse wearing masks experience this too. Everything underwater appears about 25% closer and 33% larger than it actually is. This is because the mass creates an air space in front of the eyes, and light refracts at the water-to-glass and glass-to-air boundaries. The brain interprets the angles of incoming light as if they traveled in straight lines, creating the illusion of closer, larger objects. Experienced divers learn to adjust for this, estimating distances more accurately with practice. Snorkelers and divers also experience a limited field of view due to refraction. Light entering the mass from steep angles refracts so much that it doesn't reach the eyes, creating a tunnel vision effect. Wide-angle dive masks are designed to minimize this by positioning the lenses closer to the eyes and using curved glass, but the effect can't be eliminated entirely. This is one reason diving can feel disorienting at first. The visual world is distorted, distances are deceptive, and peripheral vision is reduced. Refraction also plays a role in the colors we see underwater. Water absorbs different wavelengths of light at different rates. Red light, with its longer wavelength, is absorbed quickly, disappearing within the first few meters. Orange and yellow follow. By the time you're 10 or 20 meters deep, most of the warm colors are gone, and everything takes on a blue or blue-green tint. This isn't refraction itself, but it combines with refraction to shape the underwater visual experience. Underwater photographers use artificial lights to restore the reds and oranges, revealing the true colors of coral and fish that appear dull or monochrome in natural light. The critical angle is the angle of incidence beyond which total internal reflection occurs instead of refraction. For light traveling from water to air, the critical angle is about 48.6 degrees from the normal. If light inside the water hits the surface at an angle steeper than this, it doesn't exit into the air, it reflects back into the water. This creates a mirror-like surface when viewed from below at shallow angles. Divers looking up at a steep angle see the water's surface as a silvery mirror, reflecting the underwater scene. Only in a cone directly above, within the critical angle, can they see through to the air and sky above. This cone, called Snell's window, provides the only view out of the water. The journey through light and refraction continues now, moving deeper into the ways wavelengths interact with matter. How color emerges not just from rainbows, but from the very structure of materials, and how the bending of light reveals secrets hidden in the smallest scales and the vastest distances. When light enters a material, each wavelength slows by a different amount. This is the heart of dispersion, and it happens because light is an electromagnetic wave that interacts with the electrons in atoms. Blue light, with its shorter wavelength, is slowed more than red light in most transparent materials. This difference in speed causes the different colors to bend at slightly different angles when entering or leaving the material. The result is a spectrum, a fan of colors spreading outward, each one tracing its own path through space. Dispersion is stronger in some materials than others. Glass with high dispersion spreads colors widely, while glass with low dispersion keeps them close together. This property is measured by a number called the Abbe number. Materials with low Abbe numbers create vivid rainbows of color, while those with high Abbe numbers bend light with minimal color separation. Diamond has a particularly low Abbe number, which is why it sparkles with such intense flashes of color when light passes through its facets. The sparkle of a diamond is not just refraction, but also dispersion and reflection working together. Light enters the stone, slows, bends, separates into colors, and then reflects off the internal surfaces. The angles of those surfaces are cut precisely to send light back out toward the viewer, creating the brilliant flashes known as fire. Each flash is a tiny spectrum, a miniature rainbow born from the geometry of the cut and the physics of the material. Other gemstones also disperse light, each with its own character. Cubic zirconia has even higher dispersion than diamond, producing more colorful flashes, though it lacks diamond's hardness and rarity. Moissanite, a silicon carbide crystal, also disperses light strongly, creating a different quality of sparkle. The human eye can perceive these differences, even if the mind cannot always name them. The interplay of light and crystal structure creates a visual signature unique to each material. Dispersion also occurs in water droplets, which is why rainbows show distinct color bands. Each color exits the droplet at a slightly different angle, so when millions of droplets are present, each one contributes a single color to the arc you see. The droplet that sends red light to your eye is slightly higher in the sky than the one sending violet light. The rainbow is not a physical object, but a pattern of light, different for every observer, shaped by the geometry of angles and the physics of refraction. Beyond rainbows, dispersion creates other atmospheric phenomena. One of the most subtle is the phenomenon of atmospheric dispersion affecting the colors of the setting sun. As the sun nears the horizon, its light travels through more atmosphere, and refraction bends the light path slightly. But different colors bend by different amounts. Red light bends least, violet most. This means the sun's image is actually slightly smeared vertically into a tiny spectrum, with the red edge slightly higher than the violet edge. The effect is usually invisible because the sun is so bright and the atmosphere scatters blue light away. But careful observation or photography can reveal it. This same dispersion affects stars. When a star is near the horizon, its light passes through a thick layer of atmosphere, and the refraction causes the star to appear slightly higher than it truly is. But the dispersion also separates the colors slightly, so the star twinkles not just in brightness, but in color, flashing red, then white, then blue in rapid succession. This twinkling, or scintillation, is caused by turbulence in the atmosphere bending the light path unpredictably, and the color changes come from dispersion amplifying the effect. Astronomers must account for atmospheric refraction when measuring the positions of stars. Telescopes are often equipped with atmospheric dispersion correctors, devices that use prisms or special lenses to recombine the separated colors, sharpening the image and improving the accuracy of measurements. Without these corrections, a star's position could appear shifted by as much as half a degree when near the horizon, a significant error in precise astronomical work. Refraction also plays a role in the colors of the sky itself. While scattering is the primary cause of the sky's blue color, refraction contributes to the gradient of color from horizon to zenith. Near the horizon, light travels through more air, and refraction bends the light path, subtly altering the distribution of colors. The horizon often appears paler, almost white, because of the combined effects of scattering and refraction mixing many wavelengths together. In the ocean, refraction bends light as it enters the water, and this bending affects the colors you see underwater. Water absorbs red light more than blue, so deeper water appears increasingly blue or green. But refraction also causes objects underwater to appear closer and larger than they truly are. A fish seen from above the surface appears nearer than it is, and a person underwater looking up sees the entire above-water world compressed into a cone of light called Snell's window, a circle of brightness surrounded by the dark mirror of total internal reflection. Snell's window is a beautiful consequence of refraction and critical angle. When you are underwater and look up, light from above the surface can only reach your eyes if it strikes the water surface at an angle less than the critical angle. For water, this angle is about 48.6 degrees from the vertical. Light from any direction above the surface refracts and bends toward the vertical as it enters the water, so the entire hemisphere of the sky above compresses into a cone of about 97 degrees. Outside this cone, the surface acts as a mirror, reflecting the underwater world back to you. The boundary between the bright window and the dark mirror is sharp and striking, a geometric consequence of the refractive index of water. Photographers and filmmakers underwater must account for refraction when focusing cameras. A lens designed for air has a different focal length underwater because the refractive index difference between the lens and the surrounding medium changes. Underwater housings for cameras often include a flat port or a dome port to manage this. A flat port preserves the lens's field of view, but introduces some distortion and reduces sharpness at the edges. A dome port restores the lens's original field of view and sharpness by creating a virtual image in air in front of the lens, allowing the lens to function as if it were in air, even though it is surrounded by water. Refraction also affects sound. Those sound waves are mechanical, not electromagnetic. Sound travels faster in warmer water than in colder water, and this difference in speed causes sound waves to bend, just as light bends when crossing into a material with a different refractive index. In the ocean, temperature layers create zones where sound refracts, and this can channel sound waves over enormous distances. Submarines use this effect to remain hidden, and whales use it to communicate across hundreds of miles. The deep sound channel, a layer of water at a certain depth where sound travels farthest, is a result of refraction caused by temperature and pressure gradients. Returning to light, refraction is essential to the function of optical instruments beyond simple lenses. A microscope uses multiple lenses to magnify small objects, and each lens bends light to form an image. The objective lens, closest to the specimen, gathers light and creates a magnified real image. The eyepiece lens then magnifies that image further, allowing the eye to see details far smaller than would otherwise be possible. The total magnification is the product of the magnifications of the two lenses, and the clarity of the image depends on the quality of the glass and the precision of the shapes. High-quality microscope lenses are often made from multiple elements, each designed to correct for aberrations. Chromatic aberration, caused by dispersion, is minimized by combining lenses made from different types of glass with different dispersion properties. Spherical aberration, caused by the spherical shape of simple lenses focusing different rays to different points, is corrected by using aspheric surfaces or combinations of lenses. The result is a clear, sharp image with accurate colors, revealing the intricate structures of cells, crystals, and tiny organisms. Telescopes also rely on refraction, though many modern telescopes use mirrors instead of lenses to avoid chromatic aberration altogether. Refracting telescopes, which use lenses, were among the first telescopes ever made. Galileo's telescope used a convex objective lens to gather light and a concave eyepiece lens to magnify the image. Later, astronomers developed achromatic lenses, which combined two types of glass to reduce chromatic aberration, allowing clearer views of planets and stars. Apochromatic lenses, using 3 or more elements, reduce chromatic aberration even further, producing images with exceptional color accuracy. The largest refracting telescope ever built is the Yerkes Observatory Telescope, with an objective lens 40 inches in diameter. Building larger refracting telescopes is difficult because glass lenses sag under their own weight, distorting the image. Mirrors, which can be supported from behind, do not have this limitation, so the largest modern telescopes use mirrors instead. Still, refracting telescopes remain popular among amateur astronomers for their sharp, high-contrast images and simple, rugged design. Refraction also plays a role in binoculars, which are essentially two small refracting telescopes side by side. Prisms inside the binoculars fold the light path, making the device more compact and also flipping the image right side up. The prisms use total internal reflection to redirect the light, and their precise angles ensure that the two optical paths are perfectly aligned, so the image is seen by both eyes merge into a single three-dimensional view. The quality of the prisms and the coatings on the lenses determine the brightness and clarity of the image. Eyeglasses and contact lenses correct vision by refracting light to compensate for imperfections in the eye's own lens. A nearsighted eye focuses light in front of the retina, so a diverging lens spreads the light slightly before it enters the eye, moving the focus point back onto the retina. A far-sighted eye focuses light behind the retina, so a converging lens bends the light inward, moving the focus point forward. Astigmatism, caused by an irregularly shaped cornea, is corrected with a cylindrical lens that bends light more in one direction than another, compensating for the uneven curvature. Progressive lenses, used for presbyopia, have a gradual change in curvature from top to bottom, allowing the wearer to see clearly at multiple distances without the visible line of bifocals. The design of these lenses requires precise calculation of the refractive power at every point on the surface, and modern manufacturing techniques use computer-controlled grinding and polishing to achieve the necessary accuracy. The result is a lens that feels natural to use, with smooth transitions between near, intermediate, and far vision. Refraction also enables fiber optic communication, one of the most important technologies of the modern world. An optical fiber is a thin strand of glass or plastic with a high refractive index core, surrounded by a cladding with a lower refractive index. Light traveling through the core strikes the boundary at an angle greater than the critical angle, so it reflects back into the core rather than escaping into the cladding. This total internal reflection allows light to travel through the fiber for many kilometers with very little loss, carrying information encoded as pulses of light. Fiber optic cables carry the vast majority of internet traffic, telephone calls, and television signals across continents and under oceans. A single fiber can carry thousands of separate signals simultaneously, each on a different wavelength of light, a technique called wavelength division multiplexing. The signals are transmitted by lasers and detected by photodiodes, and the entire system relies on the precision of refraction and total internal reflection to keep the light contained and the information intact. Medical endoscopes also use optical fibers to see inside the body. A bundle of fibers carries light into the body to illuminate the area being examined, and another bundle carries the reflected light back out to a camera or eyepiece. Each fiber in the bundle transmits a single point of light, and thousands of fibers together form a complete image. The flexibility of the fibers allows the endoscope to navigate through curved passages, and the clarity of the image depends on the quality of the fibers and the precision of their alignment. Refraction also occurs in the lenses of cameras, where it shapes the light into an image on the sensor or film. A camera lens is a complex assembly of multiple glass elements, each designed to bend light in a specific way. Wide-angle lenses use strong curvature to capture a broad field of view, while telephoto lenses use longer focal lengths to magnify distant subjects. Zoom lenses change their focal length by moving elements relative to each other, altering the way light refracts through the system. The quality of a camera lens depends on how well it corrects for optical aberrations. Distortion, where straight lines appear curved, is corrected by carefully balancing the shapes and positions of the lens elements. Vignetting, where the edges of the image are darker than the center, is minimized by designing the lens to transmit light evenly across the entire image. Bokeh, the quality of the out-of-focus areas, is shaped by the number and curvature of the aperture blades and the design of the lens elements. Refraction also affects the appearance of objects seen through glass windows. A thick window can cause a slight shift in the position of objects seen through it, and if the glass is not perfectly flat, it can distort the image. Old windows, made by hand, often have slight ripples and variations in thickness, creating a wavy, dreamlike quality in the view. Modern windows are made with float glass, which is formed by floating molten glass on a bath of molten tin, creating a perfectly flat, smooth surface that refracts light uniformly. In nature, refraction creates the shimmering patterns of light seen on the bottom of a swimming pool or a shallow stream. Sunlight refracts as it enters the water, and the ripples on the surface act as moving lenses, focusing and defocusing the light. The result is a network of bright lines and dark areas that shift and dance as the water moves. This effect is called caustics, and it occurs whenever light refracts or reflects off a curved surface, concentrating in some areas and spreading out in others. Caustics can also be seen in the patterns of light on the walls of a room when sunlight reflects off a glass of water or a shiny curved surface. The light forms intricate, flowing shapes, often with a bright edge where the rays converge. These patterns are mathematically complex, and their beauty lies in the interplay of geometry and light, a visual expression of the way refraction and reflection shape the paths of countless rays. Refraction also plays a role in the formation of ice halos, circles and arcs of light that appear around the sun or moon when ice crystals are present in the atmosphere. The crystals, often hexagonal in shape, refract light as it passes through, bending it by specific angles determined by the crystal geometry. The most common halo is a circle with a radius of 22 degrees, caused by light refracting through the sides of hexagonal ice crystals. Other halos, arcs, and spots of light appear when crystals are oriented in specific ways or when light passes through different faces of the crystals. Sundogs, also called parhelia, are bright spots of light that appear on either side of the sun, often accompanied by a halo. They form when sunlight refracts through flat, hexagonal ice crystals that are falling slowly through the air with their flat faces horizontal. The refraction bends the light by about 22 degrees, and the horizontal orientation of the crystals concentrates the light into two bright spots. Sundogs are often colorful, with red on the side closest to the sun and blue on the outer side, because of dispersion within the crystals. Circumzenithal arcs are another ice crystal phenomenon, appearing as a bright, colorful arc high in the sky, above the sun. They form when sunlight enters the flat top face of a hexagonal ice crystal and exits through a side face, refracting through an angle of about 90 degrees. The arc is often described as an upside-down rainbow, but it is actually much brighter and more colorful because the refraction is more efficient and the dispersion is stronger. Circumzenithal arcs are relatively rare, requiring the sun to be low in the sky and the ice crystals to be well formed and properly oriented. Light pillars are vertical columns of light that appear above or below the sun or moon, or even above streetlights. They are not caused by refraction, but by reflection off the flat faces of ice crystals that are falling with their faces nearly horizontal. The crystals act like tiny mirrors, reflecting light toward the observer and creating the appearance of a vertical shaft of light. Light pillars are most commonly seen in cold climates when ice crystals are suspended in the air near the ground. Refraction also affects the way we see objects partially submerged in water. A straw in a glass of water appears to bend to the surface because the light from the submerged part refracts as it exits the water, changing direction and making the straw appear shifted. This is the same effect that makes a pool appear shallower than it is, and it can be surprising the first time you experience it. The brain interprets light as traveling in straight lines, so when refraction bends the light, the brain places the object in the wrong location. This effect is important for spearfishing and underwater hunting. A fish seen from above the water appears closer to the surface than it actually is, so aiming directly at the fish will cause the spear to pass above it. Experienced hunters learn to aim lower, compensating for the refraction. Similarly, a person underwater looking at an object above the surface sees it in a shifted position, and this can affect the accuracy of tasks performed across the water-air boundary. Refraction also plays a role in the colors of soap bubbles. A soap bubble is a thin film of water sandwiched between two layers of soap molecules. Light reflects off both the outer and inner surfaces of the film, and the two reflected waves interfere with each other. If the film's thickness is just right, Certain wavelengths interfere constructively, appearing bright, while others interfere destructively, appearing dark. The result is a swirling pattern of colors that changes as the film thins and thickens. Refraction within the film also plays a role, slightly altering the path of the light and contributing to the complexity of the colors. Oil slicks on water create similar colors through the same mechanism. A thin layer of oil floats on water, and light reflects off both the top and bottom surfaces of the oil layer. The interference between the two reflections creates colors that shift as the thickness of the oil changes. The colors are often vivid and iridescent, and they provide a visual clue to the thickness of the oil, with different colors corresponding to different thicknesses. Refraction is also essential to the function of the human eye itself. The cornea, the clear front surface of the eye, provides about 2/3 of the eye's refractive power, bending light as it enters. The lens, just behind the iris, provides a remaining 1/3 and also changes shape to focus on objects at different distances. This ability to change focus, called accommodation, relies on the flexibility of the lens and the action of the ciliary muscles, which squeeze the lens to make it thicker for near vision and relax to make it thinner for distant vision. The refractive power of the eye is measured in diopters, a unit that describes how strongly a lens bends light. A lens with a focal length of 1 meter has a power of 1 diopter. The human eye, with a focal length of about 17 millimeters when focused on distant objects, has a total refractive power of about 60 diopters. The cornea contributes about 40 diopters, and the lens contributes about 20 diopters, though the lens's power increases when focusing on near objects. Cataracts, a clouding of the eye's lens, reduce the amount of light reaching the retina and also scatter light, creating glare and halos around lights. Cataract surgery removes the clouded lens and replaces it with an artificial intraocular lens, restoring clear vision. The artificial lens is carefully chosen to match the refractive power needed for the individual's eye, and modern lenses can even correct for astigmatism or provide multifocal vision, reducing the need for glasses after surgery. Refraction also affects the way we see the world through tears. The tear film on the surface of the eye smooths out minor irregularities in the cornea and provides a clear, uniform surface for light to enter. When the tear film is disrupted, such as in dry eye syndrome, the surface becomes irregular and light scatters, causing blurred vision and discomfort. Blinking spreads a fresh layer of tears across the eye, restoring clarity. Refraction is also involved in the phenomenon of the green flash, a rare optical event that can occur just as the sun sets or rises. As the sun dips below the horizon, atmospheric refraction bends its light, and dispersion separates the colors. The red and orange light is refracted least and disappears first, while the blue and violet light is scattered away by the atmosphere. For a brief moment, green light, which is refracted more than red but scattered less than blue, is the last visible color. The green flash lasts only a second or two, and it requires a clear horizon and stable atmospheric conditions to be seen. It is a delicate balance of refraction, dispersion, and scattering, a fleeting gift of light and geometry. The interplay between light and matter continues to reveal itself in ways both grand and intimate. Each encounter between photon and atom, a quiet negotiation of speed and direction. When light enters a new medium, it doesn't simply slow down uniformly. Different wavelengths experience different degrees of slowing, and this wavelength-dependent change in speed is what creates dispersion. The red light at one end of the visible spectrum slows less than the violet light at the other end when passing through glass or water. This difference, measured in tiny fractions of a percent, is enough to fan the colors apart into the spectrum we recognize. The refractive index of a material tells us how much slower light travels through it compared to the vacuum of space. In a vacuum, Light moves at its maximum speed, about 299,792 kilometers per second. In water, it slows to about 3/4 of that speed, giving water a refractive index of approximately 1.33. In typical glass, light slows even more, traveling at roughly 2/3 its vacuum speed, yielding a refractive index around 1.5. Diamond, with its dense crystalline structure, slows light to less than half its vacuum speed, producing a refractive index of about 2.42. These numbers are not arbitrary. They emerge from the electromagnetic properties of the material itself, from how tightly electrons are bound to atoms, and how readily they respond to passing light waves. When we speak of light slowing down in a medium, we're describing a collective phenomenon. Individual photons don't actually slow their motion through space. Instead, they interact with the atoms in the material, being absorbed and re-emitted countless times. Each interaction takes a tiny amount of time, and the cumulative effect of these delays creates what appears to be a slower wave moving through the substance. The light that emerges from the other side of a piece of glass is not the same collection of photons that entered. It's a regenerated wave, reconstituted from the oscillations of electrons throughout the material. This process happens so seamlessly, so consistently, that we perceive continuous light passing through transparent matter. The way light bends at a boundary depends not just on the refractive indices of the two materials, but also on the angle at which the light approaches. Snell's law captures this relationship mathematically, stating that the ratio of the sines of the angles equals the ratio of the refractive indices. When light enters a denser medium at an angle, it bends toward the perpendicular to the surface. When it exits into a less dense medium, it bends away from the perpendicular. At very steep angles, when light tries to exit a dense medium into a less dense one, something remarkable happens. The light cannot escape at all. It reflects entirely back into the denser medium, a phenomenon called total internal reflection. Total internal reflection occurs when the angle of incidence exceeds a critical angle specific to the pair of materials involved. For water and air, this critical angle is about 48.6 degrees from the perpendicular. For glass and air, it's typically around 42 degrees, depending on the type of glass. Beyond these angles, the interface acts as a perfect mirror. This effect is what allows optical fibers to guide light over vast distances with minimal loss. Light entering one end of a thin glass fiber at the proper angle bounces repeatedly off the inner walls, never escaping until it emerges at the far end. Millions of such fibers bundled together can carry enormous amounts of information as pulses of light, forming the physical backbone of modern communication networks. The critical angle also explains why, when you're underwater and look up toward the surface, you see a circular window of the world above surrounded by a mirror of the depths below. This circle, called Snell's window, has an angular diameter of about 97 degrees, regardless of how deep you are. Light from above can only penetrate the surface and reach your eyes if it strikes the water surface within a certain cone. Light coming from steeper angles reflects off the underside of the surface, showing you reflections of the underwater environment instead. The boundary of Snell's window appears as a bright circle, compressed and distorted by refraction, containing the entire hemisphere of the sky and landscape above. Diamonds owe much of their legendary sparkle to total internal reflection combined with high dispersion. The critical angle for diamond is only about 24.4 degrees, much smaller than for glass or water. This means light entering a well-cut diamond bounces around, inside, many times before finding an exit path. The high refractive index also creates strong dispersion, separating white light into vivid flashes of color called fire. A skilled gem cutter positions facets to maximize these effects, ensuring that light entering from above bounces internally multiple times and exits through the top surface toward the viewer's eye, creating the brilliant display we associate with fine diamonds. Other gemstones display their own characteristic optical properties based on their refractive indices and crystal structures. Sapphire and ruby, both forms of corundum, have refractive indices around 1.76 to 1.77, producing a different quality of brilliance than diamond. Emerald, a form of beryl, has a refractive index near 1.57, closer to glass, giving it a gentler sparkle. Cubic zirconia, a synthetic diamond substitute, has a refractive index of about 2.15, high enough to produce considerable brilliance, but still noticeably different from diamond's 2.42. These differences, though seemingly small, create distinct visual signatures that trained gemologists can recognize. Some materials have refractive indices that vary with direction, a property called birefringence. Calcite, a common mineral, is strongly birefringent. When you place a clear calcite crystal over text, you see double images because light entering the crystal splits into two rays that travel at different speeds along different paths. Each ray experiences a different refractive index, depending on its polarization and direction through the crystal structure. When the rays exit, they're displaced from each other, creating two separate images. This property has been used historically in optical devices and remains important in certain scientific instruments today. The colors we see in a rainbow follow a specific order because the refractive index of water depends on wavelength. Red light, with its longer wavelength around 700 nanometers, experiences a refractive index in water of about 1.331. Violet light, with its shorter wavelength around 400 nanometers, experiences a refractive index of about 1.343. This difference of about 0.012 seems tiny, but it's enough to separate the colors by several degrees after refraction and reflection inside a raindrop. The red light exits the drop at an angle of about 42.3 degrees from the antisolar point, while violet exits at about 40.6 degrees. This 1.7 degree spread creates the width of the primary rainbow. The secondary rainbow appears at a larger angle, about 50 to 53 degrees from the antisolar point, because the light undergoes two internal reflections before exiting the raindrop. With each reflection, the light loses some intensity, making the secondary rainbow fainter than the primary. The additional reflection also reverses the order of colors, placing violet on the outside and red on the inside. Between the primary and secondary rainbows lies a darker region called Alexander's dark band, named after Alexander of Aphrodisias, who described it in the 2nd century. This band appears darker because less scattered light reaches the observer from those angles. Occasionally, observers see supernumerary arcs, faint pastel-colored bands, just inside the primary rainbow. These arise not from simple geometric optics, but from wave interference. Light waves exiting the raindrop along slightly different paths can interfere constructively or destructively, depending on wavelength. When the drops are very uniform in size, typically less than about 1 millimeter in diameter, these interference patterns become visible as delicate pink, green, and purple fringes. The spacing and number of supernumerary arcs depend on droplet size, providing a way to estimate the size of the water drops forming the rainbow. Rainbows are not actually arcs in three-dimensional space. They are sections of cones of light centered on the antisolar point, the point directly opposite the sun from your perspective. If you're on flat ground, you see only the upper portion of this cone, appearing as an arc. From an airplane or mountain, you can sometimes see more of the cone, creating a fuller arc or even a complete circle if conditions are right. The rainbow moves with you because it's defined by the geometry of sunlight, your eye position, and the water droplets. Two people standing side by side see slightly different rainbows, formed by different sets of droplets, though the rainbows appear in the same direction. The brightness and saturation of a rainbow depend on droplet size. Large drops, several millimeters across, produce bright, well-defined rainbows with vivid colors. Smaller drops create dimmer rainbows with more pastel colors and more prominent supernumerary arcs. Very small drops, those in fog or mist less than about 0.05 millimeters across, produce fog bows, nearly white arcs with faint color hints at the edges. The small size means that diffraction effects, the bending of light around tiny obstacles, become significant and smear the colors together. The result is a ghostly white arc, sometimes called a white rainbow or cloud bow, visible in mist or fog when the sun is behind you. Moonbows, rainbows produced by moonlight instead of sunlight, appear much fainter and often look nearly white to human eyes. This isn't because moon rainbows lack color, but because the light is too dim to strongly activate the color-sensitive cone cells in our retinas. In long-exposure photographs, moonbows reveal their full spectrum of colors. They're best seen during full moon nights when the moon is low in the sky and rain or spray is present opposite the moon. Waterfalls like Yosemite Falls and Victoria Falls are famous locations for moonbow viewing, where mist persists through the night. Reflection rainbows occur when sunlight reflects off a body of water before reaching raindrops. The reflected sunlight creates a second light source from a different angle, producing a rainbow that appears to originate from a point above the normal rainbow. These reflection rainbows can intersect the primary rainbow, creating unusual crossed rainbow patterns. They require specific geometry, a large, calm reflecting surface like a lake behind the observer, rain or spray in front, and the sun at the right angle. When all conditions align, the display can be spectacular and disorienting, with rainbows appearing in unexpected positions. Twinned rainbows are rare phenomena, where two rainbow arcs emerge from the same base but diverge as they rise. Unlike double rainbows, where the secondary is clearly separate and reversed, twinned rainbows have the same color order and appear to split apart. They form when raindrops of two different sizes or shapes exist in different layers along the line of sight, each group producing its own rainbow that partially overlaps. The result is a rainbow that appears to fork or split, a sight so unusual that it's often mistaken for an optical illusion or photographic artifact. Higher-order rainbows, beyond the secondary, are theoretically possible but extremely rare. The tertiary rainbow, formed by three internal reflections, appears around the sun at about 40 degrees, making it nearly impossible to see against the bright sky. The quaternary rainbow, from four reflections, appears near 45 degrees from the sun, also sunward and thus hidden in glare. In 2011, photographers using careful techniques to block direct sunlight captured the first clear images of tertiary and quaternary rainbows. These faint arcs require exceptionally clear air, uniform droplets, and precise observation techniques to detect. Circumzenithal arcs, sometimes called upside-down rainbows or Bravais arcs, appear as brilliant, colorful arcs high in the sky, centered on the zenith point directly overhead. Unlike true rainbows formed by water droplets, circumzenithal arcs form when sunlight refracts through horizontal plate-shaped ice crystals in cirrus clouds. The light enters through a vertical side face and exits through the horizontal bottom face, bending by about 46 degrees and separating into colors. Because the geometry involves refraction rather than reflection, the colors appear in the same order as a primary rainbow, with red on the outside. These arcs are relatively common, but often overlooked because people don't frequently look straight up. Circumhorizontal arcs, sometimes called fire rainbows though they're neither fire nor rainbows, appear as horizontal bands of spectral colors parallel to the horizon. They form when sunlight enters through the vertical side face of horizontal plate ice crystals and exits through the horizontal bottom face, refracting by about 90 degrees. This requires the sun to be very high in the sky, at least 58 degrees above the horizon, which limits their visibility to certain latitudes and times of year. At mid-latitudes, they're most common in summer when the sun reaches sufficient altitude. The colors are often extraordinarily vivid because the refraction angle produces strong dispersion. The 22-degree halo, a ring of light around the sun or moon, forms when light refracts through randomly oriented hexagonal ice crystals in cirrus clouds. Light entering one face of the crystal and exiting through another face 2 positions away bends by a minimum angle of about 22 degrees. This creates a bright ring at that angular distance from the sun or moon, often with a reddish inner edge and a bluish outer edge due to dispersion. The halo appears as a full circle because ice crystals in various orientations all contribute to the ring. These halos are relatively common, occurring several times per month in many locations, though people often don't notice them unless someone points them out. The 46-degree halo, larger and fainter than the 22-degree version, forms when light passes through different faces of ice crystals, entering one face and exiting through a face 3 positions away. This geometry produces a minimum deviation angle of about 46 degrees. The 46-degree halo is much rarer than the 22-degree halo, requiring more specific crystal orientations and shapes to become visible. When present, it appears as a large ring more than twice the angular size of the inner halo, often so faint that it's barely perceptible. Sundogs, also called parhelia or mock suns, appear as bright spots of light on either side of the sun, typically at the same altitude as the sun and separated by about 22 degrees. They form when sunlight refracts through hexagonal plate ice crystals that are falling with their flat faces roughly horizontal. The crystals wobble slightly as they fall, but their tendency to remain horizontal means they refract light preferentially at certain angles. When the sun is low, sundogs appear nearly 22 degrees to the left and right. As the sun rises higher, sundogs move farther from the sun, following the 22-degree halo if it's visible. Sundogs often show vivid colors, with red closest to the sun and blue trailing away. Light pillars appear as vertical columns of light extending above or below the sun, moon, or bright artificial lights. They form when light reflects off the flat faces of ice crystals that are falling with their faces horizontal. The crystals act like tiny mirrors, each reflecting light from the source toward your eye. Because the crystals are at various heights, the reflections stack vertically, creating a pillar. Light pillars from the sun typically appear at sunrise or sunset when ice crystals are present in the air. In cold climates, light pillars from street lights and other ground-based sources are common on frigid nights when ice crystals form near the ground. The green flash, a brief green coloration of the sun's upper edge just as it sets or rises, result from atmospheric refraction combined with dispersion. The atmosphere acts like a weak prism, bending different colors by slightly different amounts. Red light bends least and appears to set first. Green and blue light bend more and set last. Blue light is usually scattered away by the atmosphere, leaving green as the last visible color. The effect lasts only a second or two and requires a clear, distant horizon and stable atmospheric conditions. Over the ocean, where the horizon is sharp and distant, green flashes are most commonly observed. Blue flashes, rarer than green flashes, occur under exceptionally clear atmospheric conditions when even the blue light remains visible at the last moment of sunset. The atmosphere must be extraordinarily transparent, with minimal scattering for blue light to make it through to the observer. Some observers report violet flashes under the most pristine conditions, though these are disputed and may involve physiological effects in the eye as well as atmospheric optics. The inferior mirage, the shimmering pool of water that appears on hot roads, forms when light from the sky refracts through a layer of hot air near the ground. Hot air is less dense than cool air and has a slightly lower refractive index. Light from the sky, traveling downward and forward, gradually bends upward as it passes through progressively hotter, less dense air near the surface. The light curves upward before reaching the ground and travels back up to your eye. Your brain interprets this light as coming from a reflection on the ground, creating the illusion of water. The shimmering occurs because the hot air is turbulent, constantly changing the refractive index pattern and making the mirage flicker. Superior mirages occur when the air near the surface is colder than the air above, the opposite of the inferior mirage condition. This temperature inversion causes light to bend downward, allowing you to see objects that are actually below the horizon. Ships can appear to float above the water. Distant coastlines can become visible from impossible distances, and entire landscapes can appear elevated or inverted. These mirages are common in polar regions and over cold ocean waters where temperature inversions are frequent. The Fata Morgana, a complex form of superior mirage, can create elaborate, castle-like distortions of distant objects, stacking multiple distorted images vertically. The Novaya Zemlya effect, an extreme form of mirage, can make the sun visible even when it's geometrically several degrees below the horizon. This occurs in polar regions during winter when strong temperature inversions create atmospheric ducts that bend light dramatically. The sun appears as a distorted, elongated shape, sometimes split into segments. The effect is named after observations from Novaya Zemlya, an Arctic archipelago, where early explorers reported seeing the sun return from winter darkness several days earlier than astronomical calculations predicted. Atmospheric refraction affects the apparent position of all celestial objects near the horizon. When you see the sun sitting on the horizon at sunset, it has actually already set. The entire solar disk is geometrically below the horizon, but atmospheric refraction bends the light and lifts the sun's image by about half a degree, roughly the sun's angular diameter. This means sunrise occurs slightly earlier and sunset slightly later than they would without an atmosphere, extending daylight by several minutes. The effect is stronger at the horizon and negligible overhead, causing the sun and moon to appear slightly flattened when near the horizon, with the bottom edge lifted more than the top. Stars twinkle because atmospheric turbulence creates constantly shifting regions of slightly different density and refractive index. As starlight passes through these turbulent cells, it bends by tiny, rapidly changing amounts. The star's image shifts position slightly, and the light focuses and defocuses, causing the brightness to fluctuate. Planets twinkle much less than stars because they have measurable angular sizes. Each point on the planet's disk twinkles independently, and the combined light averages out the fluctuations. Stars, being effectively point sources of light, even through telescopes, show no such averaging, so their twinkling is pronounced. Astronomical seeing, the blurring of celestial objects caused by atmospheric turbulence, limits the resolution of ground-based telescopes. Even a perfect telescope in a turbulent atmosphere produces blurred, dancing images. The best observing sites are chosen for their stable atmospheres, often on high mountains where the air is thin and smooth. Professional observatories use adaptive optic systems that measure atmospheric distortion in real time and adjust mirror shapes hundreds of times per second to compensate, effectively removing much of the atmospheric blur and achieving nearly space telescope quality images from the ground. The Earth's atmosphere acts as a giant lens, refracting light from the sun, moon, and stars. Without this atmospheric refraction, the sky would behave quite differently. The sun would rise exactly when geometry predicts and set exactly when calculated, with no early or late adjustments. Celestial objects would maintain their true positions right down to the horizon instead of appearing lifted. the sky would transition more abruptly from day to night without the extended twilight that scattered and refracted light provides. Rainbows, halos, sundogs, and all the other atmospheric optical phenomena would vanish, leaving only the direct view of sun, moon, and stars against a darker sky. Refraction in the eye itself is what allows us to see clearly. The cornea, the transparent front surface of the eye, provides about 2/3 of the eye's total refractive power. Light entering the eye bends sharply at the air-cornea interface because the refractive index changes from 1.0 in air to about 1.376 in the cornea. The lens inside the eye provides the remaining focusing power and can change shape to adjust focus for different distances. Together, the cornea and lens refract light to form a sharp image on the retina at the back of the eye. Nearsightedness, or myopia, occurs when the eye's refractive power is too strong or the eyeball is too long, causing light to focus in front of the retina instead of on it. Distant objects appear blurred while near objects remain clear. Corrective lenses with negative refractive power, diverging lenses that are thinner in the center than at the edges, compensate by spreading light slightly before it enters the eye, moving the focus point back onto the retina. Farsightedness, or hyperopia, is the opposite condition, where the eye's refractive power is too weak or the eyeball too short. Converging lenses, thicker in the center, add refractive power to bring the focus onto the retina. Astigmatism results from uneven curvature of the cornea or lens, causing light to focus at different distances depending on orientation. A perfectly spherical cornea focuses light from all directions equally, but an astigmatic cornea is more curved in one direction than another, like the surface of football. This causes blurring and distortion that cannot be corrected by simple spherical lenses. Cylindrical lenses, which have refractive power in only one orientation, correct astigmatism by compensating for the uneven corneal curvature. Presbyopia, the gradual loss of focusing ability with age, occurs as the lens inside the eye becomes less flexible and the muscles controlling it weaken. Young eyes can easily change lens shape to focus on objects from far away to as close as a few centimeters. By middle age, the near point of clear focus has moved farther away, making it difficult to read or do close work without reading glasses. Bifocals, with different refractive powers in different zones, allow clear vision at multiple distances. Progressive lenses provide a gradual transition between distance and near corrections, avoiding the visible line of bifocals. The journey through light and refraction has carried us through angles and wavelengths, through raindrops suspended in afternoon air and crystals floating in a cold altitude where clouds turn to ice. We have watched light bend at boundaries, slow as it enters denser worlds, and emerge transformed into color and pattern. Each fact has been a small doorway opening onto the physics that shapes what we see, what we feel when we pause beneath a rainbow, what we notice when sunlight glints through a glass of water on a quiet table. And now, as we move toward rest, it feels right to reflect on how deeply woven refraction is into the fabric of our daily experience. Every glance through a window involves light bending at the glass surface. Every moment of clear vision depends on the lens in your eye refracting incoming rays to focus them precisely on your retina. The world reaches you through countless acts of bending, slowing, splitting, and recombining. Light does not travel in straight, unchanging lines through our atmosphere and our lives. It curves, it adjusts, it responds to every material it meets. When you see a rainbow, you are witnessing millions of raindrops, each performing the same delicate task. A ray enters the front surface of a droplet, refracts inward, reflects once off the back inner wall, and refracts again as it exits. The angles involved are precise. Red light exits at about 42 degrees from the direction it entered. Violet light exits at roughly 40 degrees. This small difference, just 2 degrees, is enough to separate the colors into the arc we recognize. Every droplet contributes only one color to your eye, depending on its position relative to you and the sun. The rainbow is not a thing hanging in the sky. It is a collaboration between light, water, and your specific location. Another observer standing beside you sees a slightly different set of droplets forming their own rainbow. No two people ever see exactly the same one. This idea that rainbows are personal and ephemeral adds a layer of gentleness to the physics. The mathematics are universal, but the experience is individual. The same is true for many refraction effects. The mirage you see on a hot road is yours alone, shaped by the temperature gradient in the air between your eyes and the pavement. The green flash at sunset, if you are fortunate enough to witness it, occurs because the atmosphere refracts different colors by different amounts, and for just a moment, after the red and yellow have dipped below the horizon, the green remains visible. It lasts only a second or two. It requires a clear horizon and calm air, but it is real, a direct consequence of dispersion in the layered atmosphere. There is something calming in knowing that the most beautiful optical phenomena are not mysterious or supernatural, but are instead the predictable outcomes of light interacting with matter according to simple rules. Refraction follows Snell's law. Dispersion follows from the wavelength dependence of refractive index. Total internal reflection occurs when the angle exceeds the critical value. These principles do not diminish the beauty. They deepen it. They allow us to understand why a diamond sparkles, why a fiber optic cable can carry a conversation across an ocean, why a drop of dew on a leaf can cast a tiny spectrum onto the surface below. Consider again the idea of light slowing down. In vacuum, light travels at its maximum speed, about 300 million meters per second. In water, it slows to about 3/4 of that speed. In glass, depending on the type, it slows to roughly 2/3. In diamond, it slows to less than half. This slowing is not friction. Light does not rub against atoms. Instead, the electromagnetic wave of light interacts with the electrons in the material, causing them to oscillate. These oscillating electrons re-emit light, and the combination of the original wave and the re-emitted waves produces a net effect that appears as a slower propagation speed. The light itself, the photons, still move at the speed of light in the tiny gaps between atoms. But the overall wave, the macroscopic beam, is delayed. This delay is what causes refraction. When a wavefront of light enters a denser medium at an angle, the part of the wave that enters first slows down, while the part still in the original medium continues at the faster speed. This difference in speed across the wavefront causes it to pivot, to change direction. Imagine a line of people walking from a sidewalk on a soft sand. The person who steps onto the sand first slows down, while the others are still walking quickly on the pavement. The line rotates. Light does the same. The amount of rotation depends on the difference in speed, which is captured by the refractive indices of the two materials. Air has a refractive index very close to 1. Water is about 1.33. Glass ranges from about 1.5 to 1.9. Diamond is around 2.42. The greater the refractive index, the more the light slows, and the more it bends when entering at an angle. This is why diamonds, with their high refractive index, can bend light so dramatically. When a diamond is cut with precise facets, light entering from above can be bent, reflected internally multiple times, and sent back out toward the viewer, creating the brilliance and fire that make diamonds prized. Fire, in the context of gemstones, refers specifically to dispersion, the separation of white light into colors. Diamond has strong dispersion, meaning that different wavelengths are slowed by noticeably different amounts. Blue light is slowed more than red light, so blue refracts more sharply. When light exits a diamond, the colors spread apart, creating flashes of spectral color. This is the same physics that creates rainbows, but concentrated and intensified by the geometry of the cut stone. A well-cut diamond acts as a tiny, powerful prism, splitting light again and again as it bounces between internal facets. Other gemstones also display dispersion, though usually less than diamond. Cubic zirconia, a synthetic material, actually has slightly higher dispersion than diamond, which is one reason it can be used as a simulant. Moissanite, another diamond alternative, also has strong dispersion. The interplay of refractive index, dispersion, and internal reflection determines how a gemstone will look when light passes through it. Jewelers and gem cutters use their understanding of these optical properties to design cuts that maximize beauty. Beyond gemstones, refraction shapes countless natural scenes. When you look into a calm pond, the fish appear closer to the surface than they really are. Light traveling from the fish to your eye bends as it exits the water, making the fish seem elevated. If you try to spear the fish by aiming where it appears, you would miss. The same effect occurs when you place a straw in a glass of water. The straw looks bent or broken at the water surface. The part of the straw below the surface appears shifted because the light from it refracts as it exits the water. This bending also affects how we see the sun and stars. When the sun is near the horizon, the light from it passes through a much thicker layer of atmosphere than when it is overhead. The atmosphere refracts this light, bending it slightly downward toward the ground. As a result, when you see the sun just touching the horizon, it has actually already dipped below the geometric horizon. You are seeing it in a position slightly higher than its true location. The same is true at sunrise. The sun appears before it has geometrically risen. Atmospheric refraction extends our daylight by a few minutes each day, a gentle gift from the bending of light. Stars also twinkle because of atmospheric refraction. The air is not uniform. It contains pockets of different temperatures and densities, and these pockets move and swirl. As starlight passes through this turbulent air, it is refracted slightly differently from moment to moment. The star's position appears to shift rapidly, and its brightness fluctuates. This twinkling, or scintillation, is more pronounced near the horizon, where the light passes through more atmosphere. Planets twinkle less than stars because they have a visible disk, even if small, and the light from different parts of the disk averages out the fluctuations. Stars, being point sources, show the full effect of the atmospheric turbulence. Astronomers, seeking to avoid this distortion, place telescopes on high mountains where the air is thinner and steadier, or in space, where there is no atmosphere at all. The Hubble Space Telescope, orbiting above the atmosphere, captures images of stars and galaxies without any atmospheric refraction or scintillation. The images are sharp and stable, revealing details that ground-based telescopes struggle to see. But even ground-based telescopes now use adaptive optics, systems that measure the distortion caused by the atmosphere in real time and adjust the shape of a mirror to compensate. This technology, which corrects for refraction-induced blurring, has revolutionized astronomy. The same principles of refraction that challenge astronomers also enable much of modern technology. Fiber optic cables, which carry the vast majority of internet and telephone traffic, rely on total internal reflection, a phenomenon that occurs when light tries to exit a material at too shallow an angle. If light inside a material hits the boundary at an angle greater than the critical angle, it does not refract out. Instead, it reflects perfectly back into the material. No light escapes. This allows a glass fiber to trap light inside, guiding it along even if the fiber bends and curves. A fiber optic cable consists of a core of glass with a high refractive index, surrounded by a cladding of glass with a slightly lower refractive index. Light traveling through the core hits the boundary with the cladding at a steep angle and reflects back into the core. It bounces along the length of the fiber, traveling for kilometers with very little loss. The light can carry information, encoded as rapid pulses, And because light travels so fast, the information moves at a significant fraction of the speed of light in glass. This is how a video call can travel from one continent to another in a fraction of a second. The same principle of total internal reflection is at work when you look up from underwater and see the surface as a mirror beyond a certain angle. This effect, called Snell's window, creates a circular region directly above you where you can see through the surface into the air and sky. Outside this circle, the surface reflects the underwater environment. The circle is always there, centered on the line from your eye to the point directly above. Its angular radius is about 48 degrees, determined by the critical angle for water and air. Snell's window is a beautiful example of how geometry and refraction combine to create a distinct visual experience. Mirages, too, are a consequence of refraction in layers of air with different temperatures. On a hot day, the air just above a paved road is much hotter than the air a meter or two higher. Hot air is less dense and has a slightly lower refractive index than cooler air. Light traveling downward from the sky toward the road passes through these layers and bends gradually upward. If the bending is strong enough, the light curves back up toward your eye without ever touching the road. You see an image of the sky on the road surface, which your brain interprets as a reflection in water. This is an inferior mirage, called so because the image appears below the object. Superior mirages occur when the air near the ground is colder than the air above, which can happen over cold water or ice. In this case, light curves downward, and you can see objects that are actually below the horizon. Ships can appear to float in the air. Distant coastlines can seem elevated. These mirages can be complex, with multiple distorted images stacked vertically. They have inspired legends of phantom islands and ghost ships, but they are entirely optical, the result of light bending through temperature gradients. There is a particular kind of mirage called the Fata Morgana, named after the sorceress Morgan Le Fay from Arthurian legend. It occurs when there are multiple layers of air with different temperatures, creating a complex refractive environment. Objects on the horizon are stretched, compressed, and multiplied into towering, shifting shapes. A distant boat can look like a castle. A flat island can appear as a series of vertical columns. The images change as the air moves, creating an eerie, dreamlike effect. Fata Morganas are most common in polar regions and over cold seas, where the temperature inversions are strong and stable. Even the simple act of seeing relies on refraction. The front surface of your eye, the cornea, is curved and has a higher refractive index than air. When light enters your eye, it refracts at the cornea, bending inward. The light then passes through the lens, which provides additional refraction and can change shape to adjust the focus. Together, the cornea and lens bend the light so that it converges on the retina at the back of the eye, forming a sharp image. If the eye is too long or too short, or if the cornea or lens does not refract light by the right amount, the image falls in front of or behind the retina, and vision is blurred. Eyeglasses and contact lenses correct this by adding additional refraction, bringing the focus back to the retina. The human eye is a marvel of optical engineering, but it is not unique. Many animals have eyes that use refraction to form images. Fish eyes have a nearly spherical lens with a very high refractive index, which compensates for the fact that the cornea provides little refraction underwater, since water and the corneal tissue have similar refractive indices. Birds of prey have large, powerful eyes with precise refraction, allowing them to spot small animals from great heights. Insects have compound eyes made of many tiny lenses, each forming a small image, which the brain combines into a mosaic view of the world. Even single-celled organisms can respond to light using simple refractive structures. Some algae have an eye spot, a small organelle containing pigments and a curved structure that focuses light, helping the cell detect the direction of the light source and swim toward it. This is one of the simplest examples of refraction being used for vision, and it shows how fundamental the bending of light is to life. Refraction also plays a role in the colors we see in nature beyond rainbows. The blue color of the sky, while primarily due to scattering rather than refraction, is affected by the refractive properties of air molecules. The red and orange hues of sunrise and sunset occur because the atmosphere refracts and scatters sunlight, filtering out the shorter wavelengths and allowing the longer red and orange wavelengths to dominate. The atmosphere acts as a giant filter and lens, shaping the light that reaches us. Clouds, too, interact with light through refraction and reflection. The white color of clouds comes from water droplets scattering all wavelengths of light equally. But when sunlight passes through ice crystals and high-altitude clouds, refraction can create halos, arcs, and spots of color. A 22-degree halo, a ring of light around the sun or moon, forms when light refracts through hexagonal ice crystals. The crystals act as tiny prisms, bending the light by a minimum angle of 22 degrees. This creates a circular halo at that angular distance from the sun. The halo is often faint and requires a careful eye to notice, but once you know to look for it, you may see it several times a year. Sundogs, also called parhelia, are bright spots that appear on either side of the sun, also at about 22 degrees away, but horizontally aligned. They form when plate-shaped ice crystals float with their flat faces horizontal, refracting sunlight as it passes through their sides. The refraction is similar to that in a 60-degree prism, and the result is a concentration of light at specific angles. Sundogs can be quite colorful, with red on the side closest to the sun and blue or white farther out. They are most vivid when the sun is low in the sky, and they often appear in cold weather when ice crystals are present in the air. There are many other ice crystal halos and arcs, each formed by specific orientations and shapes of crystals. The circumzenithal arc, sometimes called a smile in the sky, is an upside-down rainbow that appears high above the sun. It forms when light enters the top face of a plate crystal and exits through a side face, refracting through a 90-degree angle. The colors are vivid and pure, often more saturated than a rainbow, because the refraction is clean and the dispersion is strong. The arc is relatively rare and requires the sun to be low, below 32 degrees altitude. The 22-degree halo can sometimes be accompanied by a 46-degree halo, which is larger and fainter. This forms when light passes through the end faces of columnar ice crystals rather than the side faces. The geometry is different, and the minimum deviation angle is 46 degrees instead of 22. Both halos can appear at the same time, creating concentric rings of light around the sun. Another rare phenomenon is the light pillar, a vertical column of light that appears above or below the sun or moon. Light pillars form when light reflects off the flat faces of ice crystals that are falling slowly and fluttering like leaves. The crystals act as tiny mirrors, and if they are roughly horizontal, they reflect light from the sun or moon toward your eye. The result is a pillar of light extending vertically from the light source. Light pillars are most common in very cold weather, and they can also appear around streetlights and other artificial sources. All of these atmospheric optical effects are reminders that the air around us is not empty or inert. It is filled with water droplets, ice crystals, dust, and molecules, all interacting with light in complex ways. The sky is a canvas on which refraction, reflection, scattering, and diffraction paint ever-changing patterns. Some are common, like the blue of the sky and the colors of sunset. Others are rare and require specific conditions, like the green flash or the fata morgana. But all are rooted in the same fundamental physics, the behavior of light as it moves through materials with different optical properties. Returning to rainbows, there are details we have not yet explored. A primary rainbow, the one most commonly seen, is formed by one internal reflection inside the raindrop. But light can also reflect twice inside the drop before exiting. This creates a secondary rainbow, which appears above the primary and has its colors reversed. Red is on the inside of the secondary arc, and violet is on the outside. The secondary rainbow is fainter than the primary because some light is lost with each reflection. The angle for the secondary rainbow is about 50 to 53 degrees from the antisolar point, compared to 40 to 42 degrees for the primary. Between the primary and secondary rainbows, there is a region that appears darker than the surrounding sky. This is called Alexander's band, named after Alexander of Aphrodisias, who described it in the 2nd century. The darkness occurs because the angles between the two rainbows are not illuminated by refracted and reflected light from the raindrops. Light is concentrated just inside the primary rainbow and just outside the secondary, leaving the band between them relatively dim. Higher-order rainbows, formed by 3, 4, or more internal reflections, are theoretically possible but extremely faint and rarely seen. A tertiary rainbow, formed by 3 reflections, would appear around the sun rather than opposite it, making it nearly impossible to see against the sun's glare. Quaternary and higher-order rainbows are even fainter and have only been photographed under carefully controlled conditions. But they exist, a testament to the fact that light will continue to reflect and refract as long as the geometry allows, even if the resulting patterns are too faint for the eye to detect. Supernumerary arcs, faint bands of color just inside the primary rainbow, are caused by interference, a wave phenomenon where light waves add or cancel depending on their phase. When light exits a raindrop, waves that have traveled slightly different paths can overlap. If the waves are in phase, they reinforce each other, creating a bright band. If they are out of phase, they cancel, creating a dark band. Supernumerary arcs are most visible when the raindrops are small and uniform in size, which allows the interference pattern to be sharp and clear. They appear as pastel pink and green bands, a delicate addition to the main rainbow. Fog bows, which we have mentioned, are rainbows formed by tiny droplets in fog or mist. The droplets are so small, often just tens of microns in diameter, that diffraction becomes important. Diffraction blurs the colors together, and the fog bow appears as a broad, white or faintly colored arc. The center of the fog bow can sometimes show a slight bluish tint on the inside and a reddish tint on the outside, but the overall effect is much more subdued than a rainbow. Fog bows are sometimes called white rainbows or cloud bows, and they are most often seen in mountain fog or sea spray. Moonbows, rainbows formed by moonlight rather than sunlight, are rare and require a bright moon, typically a full moon, and rain or spray in the opposite part of the sky. Because moonlight is much dimmer than sunlight, moonbows are faint and often appear colorless to the human eye, which relies on rod cells in low light, and rod cells do not detect color well. But long exposure photographs of moonbows reveal that they do have color, the same sequence as sunlight rainbows. Moonbows are most commonly seen at waterfalls, where the spray is persistent and the moon can be bright and unobstructed. Reflected light rainbows occur when sunlight reflects off a body of water before striking raindrops. This creates a rainbow that appears higher in the sky than a normal rainbow, and it can intersect with the primary rainbow, forming an X shape. These are rare and require a large, calm body of water and rain in the right location. Reflection rainbows are a reminder that the path light takes to the raindrop matters, and even a single additional reflection can alter the geometry and create new patterns. There is also the phenomenon of twinned rainbows, where two rainbow arcs emerge from the same base but diverge as they rise. This occurs when raindrops are not perfectly spherical but are slightly flattened or have different sizes mixed together. The different shapes cause light to exit at slightly different angles, creating two overlapping but distinct arcs. Twinned rainbows are uncommon and beautiful, a visible sign of the complexity within a rain shower. All of these variations on the rainbow theme illustrate how sensitive optical phenomena are to the details of the environment. The size of the droplets, their shape, the brightness of the light source, the presence of other reflecting surfaces, all of these factors influence what you see. The physics is consistent, but the outcomes are endlessly variable. No two rain showers produce quite the same display. Refraction also plays a role in the colors of soap bubbles and oil slicks. These colors are not due to refraction alone, but to thin film interference, where light reflects off both the top and bottom surfaces of a thin layer. The two reflected waves overlap, and depending on the thickness of the film and the wavelength of the light, they can reinforce or cancel each other. This creates bands of color that shift as the thickness changes. The refractive index of the film material affects the phase of the reflected waves, so refraction is part of the process, even though interference is the main cause of the color. Caustics, the bright patterns of light that form on the bottom of a swimming pool or on a table beneath a glass of water, are also related to refraction. When light passes through a curved or wavy surface, such as the rippling surface of water, different rays are refracted by different amounts. Some rays converge, creating bright lines or spots. These are caustics, from the Greek word for burning, because the concentrated light can be intense enough to feel warm. Caustics are not a single refraction effect, but the cumulative result of many rays bending and crossing. They create intricate, shifting patterns that are mesmerizing to watch. The optics of lenses, which we have touched on, is a vast field built entirely on refraction. A converging lens, thicker in the middle than at the edges, bends parallel rays of light inward so that they meet at a focal point. A diverging lens, thinner in the middle, bends rays outward, making them appear to come from a focal point behind the lens. The power of a lens, measured in diopters, is determined by its curvature and the refractive index of the material. Glass lenses have been used for centuries, but modern lenses are often made from plastics or specialized optical materials with tailored refractive properties. Achromatic lenses, designed to minimize chromatic aberration, use two types of glass with different dispersion properties. One lens element converges the light, and the other diverges it slightly, but the two are designed so that the dispersion of one cancels the dispersion of the other. The result is a lens that brings different colors to the same focus, producing a sharper image. This principle is used in cameras, microscopes, telescopes, and eyeglasses. Microscopes use multiple lenses to magnify small objects. The objective lens, close to the specimen, forms a magnified real image, and the eyepiece lens magnifies that image further. The total magnification is the product of the two. High-quality microscopes use complex lens systems with many elements, each designed to correct for aberrations and improve image quality. Refraction is what allows us to see cells, bacteria, and even viruses, revealing a hidden world that is invisible to the naked eye. Telescopes also rely on refraction, though some use mirrors instead of lenses. Refracting telescopes use a large objective lens to gather light and focus it, and an eyepiece to magnify the image. The largest refracting telescope in the world, at Yerkes Observatory, has an objective lens 1 meter in diameter. Larger lenses are difficult to make because glass is heavy and can sag under its own weight, distorting the image. Reflecting telescopes, which use mirrors, can be made much larger, but refraction still plays a role in the eyepiece and in correcting optical aberrations. Cameras, too, are built around lenses that refract light to form an image on a sensor or film. The aperture controls how much light enters, and the focal length determines the field of view and magnification. A wide-angle lens has a short focal length and a broad field of view. while a telephoto lens has a long focal length and a narrow field of view, magnifying distant objects. The quality of a camera lens depends on how well it manages refraction, minimizing distortions and aberrations while maximizing sharpness and contrast. Even the humble magnifying glass is a tool of refraction. It is a simple converging lens that forms a virtual image of an object, making it appear larger. When you hold a magnifying glass close to something and look through it, the lens refracts light from the object so that the rays entering your eye appear to come from a larger, closer object. Your eye focuses on this virtual image, and you perceive the object as magnified. It is a straightforward application of refraction, but it has been transformative, enabling detailed examination of everything from insects to manuscripts. The principles of refraction extend into the realm of optical instruments used in medicine. Endoscopes, which allow doctors to see inside the body, use fiber optics to carry light in and images out. The fibers rely on total internal reflection to guide light through narrow, flexible tubes. Lasers, used in surgery and other medical applications, are focused using lenses that refract the intense beam to a precise point. The cornea and lens of the eye can be reshaped using lasers, correcting refractive errors and reducing the need for glasses. This procedure, called LASIK, involves carefully ablating tissue to change the curvature and thus the refractive power of the cornea. Refraction is also central to spectrometry, the analysis of light to determine the composition of materials. When light passes through a prism or a diffraction grating, it is separated into its component wavelengths. Each element and molecule absorbs and emits light at specific wavelengths, creating a unique spectral signature. By measuring these wavelengths, scientists can identify substances, measure temperatures, determine velocities, and explore the properties of distant stars and galaxies. Spectrometry relies on the precise control and measurement of refraction and dispersion. In the field of fiber optics, not only is light guided through cables, but it is also manipulated in complex ways. Wavelength division multiplexing allows multiple signals, each at a different wavelength, to travel through the same fiber simultaneously. This is possible because the refractive properties of the fiber and the devices that launch and receive the light can be tuned to handle many wavelengths at once. A single fiber can carry terabits of data per second, enough for millions of simultaneous phone calls or video streams. This capacity is what makes modern internet infrastructure possible. Optical switches and routers, which direct light signals through networks, also use refraction. Some switches use tiny movable mirrors or prisms to redirect light from one fiber to another. Others use materials whose refractive index can be changed by applying an electric field, allowing light to be steered without moving parts. These devices are fast, reliable, and energy efficient, and they form the backbone of global communication networks. Refraction even plays a role in art and design. Stained glass windows, which have adorned cathedrals and buildings for centuries, use colored glass to filter and refract light, creating patterns and images that glow when backlit by the sun. The colors come from metal oxides and other additives in the glass, which absorb certain wavelengths and transmit others. The refraction to glass surfaces can create subtle shifts in color and brightness, adding depth and richness to the images. Prisms and lenses are used in stage lighting and photography to shape and color light. Gobas, metal or glass templates placed in front of lights, project patterns, and lenses focus and spread the light to create the desired effect. The interplay of refraction, color, and shadow is a tool for storytelling and mood, used in theater, film, and architecture. Rainbows themselves have inspired art, literature, and music throughout human history. They appear in myths and religious texts as symbols of hope, promise, and divine presence. The rainbow is a bridge, a sign, a moment of beauty in the midst of storm. Understanding the physics behind the rainbow does not diminish its power. If anything, it deepens the appreciation, revealing that this symbol of wonder is also a demonstration of universal laws, a visible proof that light and matter interact in orderly, predictable, beautiful ways. The journey through refraction and rainbows has taken us from the fundamental bending of light at a boundary, through the mathematics of Snell's law and the wavelength dependence of refractive index, to the myriad phenomena that result. We have seen how rainbows form, why diamonds sparkle, how fiber optics work, why mirages appear, and how the sky displays halos and arcs. We have explored the role of refraction in vision, in telescopes and microscopes, in cameras and eyeglasses. We have touched on the way refraction shapes our perception of the world, from the fish in the pond to the stars in the sky. Each fact, each example, is a thread in a larger tapestry. Refraction is not an isolated curiosity, but a fundamental aspect of how light moves through the universe. It is present in every transparent material, every boundary between media, every moment when light changes speed. It is the reason we can see clearly, the reason we can communicate across vast distances, the reason the sky is full of color and pattern. And as you rest now, your mind can hold these ideas gently. You do not need to remember every detail, every angle, every name. The essence is enough. Light bends, colors separate, patterns emerge. The world is filled with refraction, quietly shaping what we see, connecting us to the physics that underlies all of nature. If you are still awake, there are other journeys waiting, other topics to explore in this same calm, steady way. The universe is full of phenomena that invite curiosity and wonder, and each can be unfolded slowly, with care, allowing the mind to wander and rest at the same time. But if sleep is calling, that is good too. Let the images of rainbows and light fade softly. Let your breathing deepen. Let your thoughts drift. The rainbows will still be there, in the rain and the spray, in the prisms and the dewdrops, waiting for the next time you look up and see the light transformed. The physics will still be there, reliable and beautiful, a foundation you can return to whenever you wish. And for now, you can simply rest, knowing that the world is full of light, bending and splitting and painting the air with color, even as you close your eyes.